Hello, this is Bhavesh Jain, and I have Akshit Khandelwal and Abhay Kumar with me as my teammates for the project on bacterial chemotaxis, which is basically a course project for the course Engineering Analysis and Process Modeling. This project is basically a modeling simulation of the phenomena bacterial chemotaxis. So, what are the objectives of the project? It is to simulate the movement of a particular bacteria in response to a sugar concentration and output the position of bacteria with respect to time, and also to find out the time required to the bacteria to reach the sugar particle from origin. And the key assumptions made during the simulation was the shape of the bacteria to be round and point in size, the concentration of sugar at radius 0 is constant throughout the simulation. Concentration of sugar increases radially with time following the Fick's law of diffusion, and two-dimension diffusion is considered. Also, if the bacteria is zero point 0.5 units near the sugar, we will consider that it has reached the destination. A minimum number of flagella of bacteria must be activated, that is, the receptors must be activated to start the run and tumble motion, which is a major part of our simulation. So, moving on to next slide, what is bacterial chemotaxis? In basic terms, we can say the movement of bacteria to a higher concentration of a particular chemical, and its motion is termed as bacterial chemotaxis. It involves sensing of nutrients by the bacteria through the receptors, which we are calling flagella, and towards it uh, navigate towards it. Bacteria adjust their movement by modulating flangeral rotation. Directional movement is crucial for bacteria to find its nutrients, that is, the tremble motion. So, the major part of this simulation is run and tremble motion, and the overall movement of bacteria is basically divided into two parts. First is run, which is basically a straight line motion of the bacteria, and then the tremble, which is a reorientation of bacteria i- in its particular position. So, as the result of the trajectory of bacteria swimming in a uniform environment, it will be a random walk with relatively straight motion in line. And what is this random walk or random tremble movement? It is basically governed by the probability curve. What is Bell's probability curve and why the motion is random but not so random will be explained later. So now we were talking about what is this random walk of the bacteria towards nutrient and why it is not so random. So according to Bell's probability curve, it will move it will move towards the nutrient, and it has probability highest to move towards the nutrient and lowest to move away from the nutrient. And we can see that the 0.43 probability is where the bacteria wants to go, and in opposite direction it has probability 0. All these probabilities are derived from the Bell's probability distribution curve, which was shown earlier, and we are taking the assumption that the bacteria in our simulation can only move in 8 possible directions, and all the probabilities are shown here. Next, we have Fick's law of diffusion. So you might have a question that how are we gonna determine the concentration of sugar at different point in two dimension and in different time scale. So it is governed by Fick's second law that predicts how diffusion will cause the concentration change with respect to time. So Fick's law is a partial differential equation of second order, where in this equation we can see that phi is concentration, d is diffusion constant, t is time, and delta is double partial derivation of concentration with respect to x. On solving this equation, we can get the solution of Fick's law of diffusion, which you can see in front of you. In this, if we assume that the concentration at the point where radius is 0 is constant. So after solving the Fick's equation, with this assumption, we can get the equation of concentration equals to initial concentration multiplied by exponential of minus r square by 4 dt, where r is radial distance and c naught is the initial concentration of sugar and d being diffusion constant. Using this equation, we can find the concentration at any point at given time in any 2D space. And we have used this equation for our simulation. As we can see how diffusion takes place in this two-dimensional area, we can see in the figure, as we put the sugar, it slowly starts diffusing in a two-dimensional space, and the concentration at any point increases with time, and also it decreases radially. We can see that the initial phase of diffusion, uh, the radial distance, which is very far away from the center, has a very less concentration, and with time it increases. Next, Akshat will continue the presentation.
So we will now discuss the relation between flagella and concentration. We assume that increasing the concentration will increase the percentage of activated flagella. We are using percentage of activated flagella is equals to 200 upon e to the power minus of 0.022 upon concentration plus 1 minus 100. The reason of assuming this expression is when the concentration is 0, the percentage of activated flagella is 0. And when the concentration is approaching infinity, the concentration is approaching infinity, the percentage approaching 200. Now, let's discuss the relation between velocity and activated flagella. We assume that linear relationship between velocity of bacteria and percentage of activated flagella. The relation of velocity of bacteria is equals to velocity constant time percentage of activated flagella minus minimum number of activated flagella required to move the bacteria. It can be noted that the velocity will increase till a certain limit and it will be constant once the percentage of activated flagella reaches 100%. Now, let's discuss the process how we calculate the position of bacteria with time. At first, we will calculate the minimum concentration required to move the bacteria. Now, after zero point 0.5 second, we will check the concentration of food at the coordinate where bacteria is present. After finding the concentration, we will calculate the velocity of bacteria for that zero point 0.5 seconds. Using the run and tumble approach and normal distribution curve, we will calculate the direction of bacteria. Now we know the direction in which the bacteria will move and the velocity of bacteria for next zero point 0.5 second. We will calculate the position of bacteria after half seconds and do the same process again and again till the bacteria reaches the food. This is the result of our simulation where you can see that the bacteria is not moving straight forward. It is moving, it is tumbling, and after 35 steps, it will reach the food. Now we will demonstrate how to calculate how we calculate the how we simulate this result. So this is the code we have write for the calculation of position of bacteria with time. Let's run this code. So here we get the output.txt file which contain all the coordinates with time. This is the first integer is the time, and the second and third values are coordinates of the bacteria at that time. Now let's plot the curve. This is the curve we get. As you can see, the bacteria is again tumbling and finally reach the position. Thank you.